Just like whenever we had our equations, we could solve those and we could determine whether they would always, never, or sometimes have a solution. You can do the same thing with inequalities. In problem A there, you're just going to distribute. And then if possible, you want to eliminate your variable. So I'll add 6 to both sides, 6x, and when you do that, you have the inverse operations happening here. You're adding the opposite. They make 0, so you have -2 is greater than 7. Is that a true statement? No, absolutely not. And since that is a false statement, we're never going to have an answer. Meaning it doesn't matter what variable you would choose to put in this inequality, it would not come out as a true statement. Problem B, distribute your 5. Once you combine your like terms, you can see that you've got 3x on both sides of the inequality. So you can subtract that. -15 is less than or equal to 8. Is that a true statement? Yes, that's a true statement. A negative is less than or equal to 8? Yeah. Because we're saying, is it less than or equal to? It doesn't have to be both. Yes, -15 is definitely less than 8. That's a true statement. So you are always going to have an answer here. And then for part C, you're going to realize that when you try to eliminate your variable, you can't. But what you can do is you can solve for it, and you can get that x has to be greater than 4. So will we always, never, or sometimes have a solution here? Selena? Very good. Selena, do you want to tell me when those times will be?
When x is greater than 4.
Exactly. If you pick anything less than 4, it's not going to work as a solution to this inequality. The new thing that we're doing today are compound inequalities. What compound inequalities are? They are two inequalities joined by either the word and or. Let's think about this. I asked you to go to Sheetz and buy me an iced tea and a Dr. Pepper. Am I going to be happy if you come back with one of those? No. I want an iced tea and a Dr. Pepper. I want both. Both things have to be satisfied because I said I want this and that. There were two things that needed to be satisfied in order to make me happy. An and inequality is just like that. Both inequalities have to be true. What is the solution of 7 less than 2x plus 1 and 3x less than or equal to 18? This is a compound inequality joined by the word and. You just solve both inequalities separately. So start with 7 less than 2x plus 1. So 3 is less than x, which is the exact same as saying that x is greater than 3. I'm just reversing the sides of x and 3. And now I'm going to graph that just like we did yesterday. And you'll see why, but what I'm going to do, instead of making my line exactly on the number line, I'm going to make it a little bit above it. And you'll see why in a second. And my other inequality, 3x is less than or equal to 18. I can solve that. X is less than or equal to 6. Graph it. Now what we're saying is both things have to be true here. X has to be greater than 3 and x has to be less than or equal to 6. So what you want to think about is, where would my solution be? Where are both of these inequalities true? The nice thing about this is that you have the color overlapping anywhere it's true. Cameron, what were you going to tell me?
That x would have to be either 4 or 5.
Good. 4 and 5 would work because both inequalities are true there. What about 3? Would 3 work? No, that's an open circle. What about 6? Yes, it is a closed circle, so our x is less than or equal to 6. That's true. And then as you can see, x is greater than 3. That includes the 6. So since that's a closed circle and it's included in the x is greater than 3 inequality, that would be true. So now my final answer here, I have an open circle at 3, a closed circle at 6, and I shade in between. And you don't have to erase these other lines as long as you're specific with where you're shading. That would be your solution to this inequality. It is written as x is, now you're reading backwards, x is greater than 3 and x is less than or equal to 6. What's the solution to 5 less than or equal to 3x minus 1 and 2x less than 12? So again, we're dealing with an and inequality here. Do the exact same thing that we did before. Solve your equation, your inequalities separately. So you get that x is greater than or equal to 2. (2x less than 12). You have that x is less than 6. By graphing both of those, you can see that anywhere that both of them are true is going to be a solution. Should we include 2? Yes. Should we include 6? No. So we will fill in 2, open circle at 6, and our shading goes in between. And then we will write it as x is, read backwards, x is greater than or equal to 2. And now when you read the right side, it's just going to be how we usually read it. X is less than 6. What about part B there? It says, is that compound inequality of problem 5 always, sometimes, or never true? What do you guys think? Always, sometimes, never. Cameron?
Sometimes.
Exactly. What times will it be true? Go ahead, Cameron.
When it's 2, 3, 4, 5.
Right, when it is in between 2 and 6. When we have that solution, it is sometimes true. If we pick something outside of that solution, it's not going to be true. Here's a fun one. Example C. Solve both of your inequalities. So x is greater than 2. And don't forget to flip your sign because you're dividing by this -3. X is less than -3. What's the solution to this compound inequality? X greater than 2 and x less than -3. Jordan.
-3 is greater than x, which is greater than 2.
Not quite, because we have our arrows going in the opposite directions. You'd have to switch that sign.
Oh.
That's why. Julius.
There's no solution.
Absolutely. Wonderful. Math high five. No solution. This is a special case. There is nowhere on this graph where both of these inequalities are true at the same time. So there's no solution. Alrighty, now you're going to sheets again. And I told you that now I want an iced tea or a Dr. Pepper. Will I be okay if you come back and only give me an iced tea?
Yes.
Yes. And you can feel free to do that anytime you want. I really like iced tea. And will I be okay if you come back and just give me a Dr. Pepper? Yeah, I'll be all right with that. I like Dr. Pepper too. Will I be okay if you come back and you give me both? Sure, that's wonderful. But when I'm using the word or, I want this or that. I only need one of them. And in our inequalities, when we have or inequalities, only one thing has to be true. Both inequalities can be true. That's like a bonus. But I need at least one inequality true. So with the or inequalities, you're dealing with at least one true inequality. So we have these two inequalities separated by the word, or I guess we should say joined by the word or. Solve both of them. You get k is greater than or equal to -1. Go ahead and graph that. Guys, I'm crazy. That's less than. You, Chen, is that what you were going to tell me?
Yeah.
Thank you. Woo, now we're multicolored. Alrighty. Greater than or equal to -1. That's better. And then for the next one, k is less than -5. And guess what, guys? That's our solution. That's all we have to do. Only one of these inequalities has to be true. So anywhere you have the blue line, anywhere you have a red line, those are solutions to your equation. Can somebody tell me what would not be a solution here? Give me some examples of numbers that would not be a solution. Alex?
-3.
Very good. -4, -2. All of those are in the not a solution section. Everything else is a solution. Yeah, you can just circle the k is greater than or equal to -1 or k is less than -5. Oh, here's another fun one. Solve both inequalities joined by or. So I'm going to subtract 25 from both sides. 10x is greater than -50. X is greater than -5. Why didn't I flip the sign there? I got a negative answer. Why didn't I flip the sign? Morgan?
Because you divided by +2.
Good. Only when you divide by the negative are you switching the sign. And then on the other side, I'm adding 1 to both sides. 4y less than -12. So w is less than -3. What's your solution to this inequality? Jess?
-4.
It could be -4. You're right. What else could it be? Remember, this is an or inequality. So we either need x is greater than -5 or x is less than -3. Only one has to be true at a time. Jess?
Anything.
Anything. And in math, we can say all real numbers. Sometimes our real numbers are labeled with this big capital R. Because everywhere on this graph is a solution. If you look at the colors, everywhere on this graph has a color on it. Gabby?
What would you want us to put as an answer on the test?
All real numbers.
What if it wasn't on the numbers, just an or inequality?
You would just put like x is greater than 7 or x is less than -2. You would just write it out. Good question. And let's finish up with example B. We've got 15 less than 5x. So 3 is less than x. And I like to switch that to say x is greater than 3. And you also get that x is less than -1. And remember, we have an or inequality, so that means either one or the other has to be true. Both don't have to be true. So those are our answers. Either x is less than -1 or x is greater than 3.